Berlin. Volker does not need any presentation. He has done work in this year which had a profound impact in many fields of numerical analysis, and not only, particularly in numerical linear algebra, in control theory, differential algebraic equation. And recently, he is a pioneer of port-Hamiltonian system, which is an emerging, very important field, which will be the subject of today. Volker has received many awards, particularly this year he is European Mathematical Society Distinguished Lecturer. So we can consider this a distinguished lecturer of the European Mathematical Society of Volker this year. He has been president of the European Mathematical Society formerly, till 2022, and before he was president of GAM. He is a science fellow, American Mathematical Society fellow. He got the Schneider Prize, and Schneider Prize, ILAS. So I continue for a long time, but I prefer to invite him to speak to us about the Hamiltonian system. Thank you very much, Volker, for coming, and thank you very much to all of you for being here.
Yes, thank you very much for the invitation to come to Latvia again. And I see a lot of people back, very few people in front. So if that means that you're shy, don't be shy in asking questions. So we have some time. Please ask questions if you don't like. Try to make the talk very elementary in the sense that I try to send you a message rather than to be all the thing. It's I know. So I will talk about, as Ola said, port-Hamiltonian systems, and I will tell you what they are and why they are so important. But I will also talk a little bit about representations. Representations in the sense that we would like to have a representation that is good from an analytical point of view, but also good from a numerical point. So that when you simulate or control these systems, you don't make too many errors. Okay. So in the last 20 years, we've been working using the theory of port-Hamiltonian systems, which started around 2000. Mainly by work by Ian Wanderschaft and Bernard Maschke. Wanderschaft from Groningen and Bernard Maschke from Lyon. And we have been using this in all kinds of applications. So, for example, in gas transport networks, there's a big CRC, research center in Germany, about 2 million euros per year on gas transport. We have been working on district heating networks. So I don't know whether this is in Italy, but so you heat centrally and you heat water and chicken. That was it. District heating, electrical circuits, turbulent flow, magnetohydrodynamics. Big topic right now, today, there's a meeting. The French want to put up new nuclear power plants everywhere. Germany doesn't want to do this, but we have lots of wind and solar, and that creates a lot of problems for the mathematical problems for the stability, and a lot more. And let me give you one example, which comes from power systems. So that was also a priority program, and Columbia Research Center was in physics department. The topic was theoretical methods and concepts for self-organizing non-linear systems. And we worked on delay differential equations. And together with electrical engineering people, we worked on these mixed systems with electrical systems, with photovoltaics, wind, classical gas power plants, coal power plants. And the question how to combine them in a good way so that we don't have top-down breakdown of power very much. So here is the simplest power system that you can think of. So Rg, Rl, and Rr are the resistances. L is an inductor. C1 and C2 are capacitances, and Eg is a voltage source. And when you write down, there's a little circuit which describes such a simple surrogate model of a DC generator connected to a load via a transmission line. So that's one of the simplest versions of a power system that we can write down. And it consists of differential equations. Li dot, I is the current, linear differential equation for I, linear differential equations for V1, which is the voltage here, another differential equation for the voltage V2, plus two algebraic equations. And they come from Kirchhoff's laws. So when you model a electrical circuit or power system, you get a nonlinear set of differential equations plus algebra. So that is what you can think about. And clearly, when you have these algebraic equations, you could solve for V1 and V2, insert it into the other equation, then you have an ODE. And this has been the way mathematics dealt with it until 1865, when Kirchhoff wrote down these type of equations, and he was Academy of Science in Berlin, and he said, can somebody give me an algebraic analysis of such equations? And Weierstrass and Kronecker both were in the audience, and they created canonical forms for these guys, the linear. And then this was forgotten until 70s, when automatic modeling with SPICE or other modeling packages of electrical circuits came about, and there were too many equations, so that you could not go by hand insert things. Started to think about this in more automatic action. So, with all these applications from different domains in mind, you could ask the question, hey, you're a mathematician, what do we want from a mathematical model? Well, we want a model that is close to physics. But not only for closed systems, but also for open systems, so that we can do control. We want representations that allows us to couple models of different scales and from different physical domains. And the model class should have nice algebraic, geometric, and analytical properties. The model should be easy to analyze mathematically, existence, uniqueness, robustness, and also stability and passivity, and this will be a big part of my talk. We talk about stability and passivity. We also want what Kirchhoff asked Weierstrass and Kronecker are the canonical forms under which I can understand the solution behavior. And then the model class should be good for space and time discretization, numerical analysis, and model reduction. And it should be usable in simulation, control, optimization. And in Germany, there's a word for this. It's called eierlegende Wollmilchsau. Egg, laying, wool, milk, saw. It's a perfect animal vision. It was everything. In English, it's called Swiss Army knife or jack of all trades. So, can there be such a mathematical model? And around 2000, my two colleagues started to do something like that. And so they said, okay, if we want to couple different physical systems, what choice do we have? The only link or fragile to couple different parts of physics would be electrical power. So to couple mechanical, hydraulic, electrical, chemical, thermal systems, the only thing you can do to switch between the systems will be transport. So they had the idea is to split the network of systems into energy storage elements. Energy storage is, for example, mass stores energy, or capacitance, or whatever. And then there are energy dissipation components, like areas where you have friction, and the friction leads to taking energy and turning it into heat. And we also want to have control in inputs and control outputs, as well as interconnections. And this is essentially a contribution that we did in the last years, is we allow every model not only to be one model, but a whole model catalog or hierarchy. And these could be fine, of course, discretized models in the PDE setting, continuous models, discrete models, full models, reduced models, and actually, if in the automobile industry is now the hardware in the loop, so we could even have a machine which put there, which the measurements are used in. And the system theoretic approach to deal with this is called port-Hamiltonian systems. Here in this talk, I will concentrate on finite dimensional port-Hamiltonian systems, but there's a whole extension to the theory to infinite dimension, even though there the notation, everything is not 100% unified. Okay, so what is a classical port? It's an ODE. X dot equals J of X and T, and J is a stereosymmetric matrix that describes the flux of energy between the different elements that's stored. In most cases, it is a symplectic matrix, 0 identity minus identity 0, but it could be an arbitrary stereosymmetric matrix, and it could depend on the state and also on time. And then we have R. R is a symmetric positive semi-definite matrix or matrix function, which describes the energy dissipation or loss system. And then there's a function H, which is the Hamiltonian, and describes the distribution of internal energy among the energy storage elements. It's a function, a real that maps into the state space into the real, and here we take the gradient of that function. So without the rest of this, this is a classical Hamiltonian system. Maybe the coefficients are a little bit more general, but classical Hamiltonian system is a special case. And now we also add inputs. So we add matrices for E and P times an input U, and we add an output. And the output is special. It's collocated in the sense that it has a second dimension, so that you can form an inner product between the input and the output, and that will be the supply energy in the supply system. And there could be a term here, a so-called feed-through term, and I split it into symmetric and asymmetric part. The P plus minus P are ports where energy can enter the system from one side or go out to the other. In order to deal with most realistic systems, we have to add algebraic constraints. And then we get not port-Hamiltonian ODE systems, but differential algebraic systems. That will be on the next slide. So it looks exactly the same, except now we have a matrix function here in front of the dot, and that could be a singular function to deal with algebraic equations. And instead of the Hamiltonian, the gradient of the Hamiltonian, I put another function E, which is usually called the effort. And then there is this function R of T of X, which is mainly needed to deal with time varying state space transformations. So if E is the identity, R is 0, and little e is the gradient of the Hamiltonian, we're back in the previous model. And what else do we need? We need that J is skew-symmetric and the skew-symmetric that's automatic, but that the matrix W, which is R, E, E transpose S, which is a symmetrical particle, that this is pointwise positive semi-definite, denoted by greater or equal to 0. And we have that the gradient of the Hamiltonian is E transpose times little e. So E is the identity, and we just have the old representation back. And the time derivative, that's when. So if the Hamiltonian is not explicitly depending on time, R is just 0. So this is work done by my appreciation to recovery what I finished 2 years ago. And he extended most of the stuff to this differential algebra. So why are we interested in this class of port-Hamiltonians? First of all, they generalize classical Hamiltonians. That's big class physics. They also generalize so-called gradient systems, mainly used in thermodynamics. We don't have conservation of energy, but the conservation of energy is replaced by a so-called power balance equation. I have one slide. A really cool thing about port-Hamiltonian system is that if you take 2 port-Hamiltonian systems and connect them in a power conserving way, then you can get one. That means you can play Lego. So you can have a port-Hamiltonian system. One physical domain, one second physical domain, and you can interconnect them in an energy or power conserving way, and you can get one. You can go to weak formulation in the PDE setting and do galactic projection, and it will preserve. And the physics is encoded in the algebraic structure of the coefficient, the geometric structure of the flow. You also get discontinuity, semi-discontinuity, and stability, because this H is a candidate for the Lyapunov function. So usually in ODEs you have to work hard to find the Lyapunov function. Here it's given. And just to tell you what a system, the usual definition of passivity is, the system is called passive if for some energy supply function, which is function of y and u, there exists a storage function h such that the dissipation, that's the general definition, but I will have another more easy definition. So I mentioned already this power balance equation. So what does it say? It says that the total derivative of the Hamiltonian function with respect to time is given by EU, this joint vector, multiplied with this W function, which was positive semi-diff. And as a consequence, this term here is negative. And then we have Y transpose U, or the inner product, the dual parent between Y and U if you're in an infinite dimensional setting. This is the dissipating energy, and this is the supplied energy. And this balance equation holds along any solution for any input. And in particular, when you drop this term, because it's negative, then we get the dissipation. And that means automatically by this definition, such a system is passive, but it may not be strictly passive. The second thing is you can make the system autonomous without destroying the structure. So you can get rid of the T dependence by introducing T dot equals 1 as a new variable. That's a usually trick that we do only is to make things autonomous. It will not change the Hamiltonian polynomial structure. And you can interconnect. So if you take two such systems with Hamiltonians HI, and you take now an aggregated input U1 and U2 and an aggregated output Y1 and Y2, and you do any linear or nonlinear combination of the U's and the Y's, then the new system is again a port-Hamiltonian system, the Hamiltonians again. So this is really nice modeling, because as an engineer, you would like to model the electrical engineer models the electrical part, the mechanical engineer models the mechanical part, and then they're stuck together. The nice thing is interconnection still works if you use different state models, because the interconnection is only involving U and Y and not X. And as a consequence, you could have a very fine model 3D PDE for X, or so-called model 2x2 polygon. This slide is just not to confuse you, it's just if we do state space transformation, different morphisms that map X to phi of T and X tilde and multiply with non-singular pointwise non-singular matrices, then we get again a port-Hamiltonian system. And if the diffeomorphism is global, then the systems are one-to-one. So that means you can do canonical forming. And I will come back to this later on when I talk about representations. But this is a fully nonlinear version that you can do changes in state space and also changes in the equation, and it will stay in the structure. So I love port-Hamiltonian systems. And there's a meta theorem. Whatever you want to have a dynamical system, if you try it for port-Hamiltonian system, it works. So it's really magic. And the part that I will talk about now is stability and passivity. And again, to analyze stability and passivity, port-Hamiltonian structure works extremely nice. So why are we interested in stability and passivity? Most real-world systems are internally stable. If you don't add anything, not excite them, they go to equilibrium. And however, before they go to an equilibrium, there may be an initial transient phase where the solutions grow very large. Lactula is one, for example, for that, whether the transient phase very big deviations, and unfortunately, stuff was destroyed. So transient growth may lead to catastrophe. most systems with inputs and outputs are passive. That means they don't generate energy from inside. Real physical systems typically dissipate energy since friction and damping is everywhere. And so without supply of energy, they relax into equilibrium. But if I just give you an ODE or a PDE, the stability and passivity are very hard to check because we need to construct. So let's go back to the first course on differential equations. So I have x dot equals f of t and x. So initial value x0. Then we say it's stable if for epsilon greater than 0, there exists a delta greater than 0, such that the initial value problem with a perturbed initial condition close to the old initial condition. The solution for this initial condition stays close to epsilon close to this. And it's called asymptotically stable if then the limit for t to infinity goes to 0. And exponentially stable if we even have a bound, which would be the case next one. Classical definition, we can always assume that the initial point is 0, and in most cases, you can also assume that the equilibrium solution of the system is 0. So if you go to your first course on differential equations, there are really many different ways to study solution. In the linear case, and also in the nonlinear case, locally you do matrix formula. You look at eigenvalues of the matrix or the operator, and if they're all in the left half plane, then there's also the field of values, which is x transpose AX for all vectors x elements that exist, either values in the left half plane, you'll find them. There's also so-called pseudo-spectral abscissa, which is spectrum under perturbations. And one can also look at e to the AT in the linear case, which is the operator. And there's also the concept of hypercoercivity, which I will touch a little bit later. The nonlinear case, essentially no other choice than creating the optimal function. And then you have to study the decay, the erosive solution, bifurcations, stuff like that. And port-Hamiltonian systems provide a very good representation. But I need first recall the optimal function. So suppose we have an autonomous ODE that equals cube z with equilibrium solution tilde. Then we can assume that this z tilde is equal to 0 by looking at the difference to that. Then, if you have an autonomous system with equilibrium solution x tilde, if one can construct a function v, which is greater or equal to 0 for all states, and in a boundary in a ball around 0, but not at 0 directly. At 0 it's 0, at x tilde it's 0, if only x tilde is 0, and the derivative of the function with respect to time can be expressed as the gradient times b f of x. That's less than or equal to 0 for all points in this ball. This is called the Lyapunov function. And if the inequality is strict here, then it's called just strict again. It's extremely difficult for a general nonlinear system to derive a Lyapunov function. But there's the following theorem of Lyapunov, 120 years old. If an autonomous system is equilibrium 0, there exists a Lyapunov function that the system is stable and if there is a strict Lyapunov function, it's asymptotic. Classic result. Local in the neighborhood of lower equilibrium, whether the Lyapunov function exists. To get global asymptotic stability, you need extra condition. It's like sectoriality or radial unboundedness and so on. Let me go reading so. So this we'll learn in a course. And so what do we have here? So in the linear case, there exists typically quadratic. P of x is 1/2 x conjugate transpose qx, where q is emission and positive definite, and it's a solution of such a Lyapunov inequality. Because if we have such a q, and we take that function, and we differentiate, take the product rule here, and then we pull out the xh, and then we get this, and this is less than or equal, less than 0 for x. So in the linear case, we can construct such Lyapunov functions, and since q is positive, definitely defines a norm. It's a weight norm from the 2 norm, which you can use to study the behavior. And so if it's less than or equal, then it's stable, and if it's less than 0, then it's stable. Okay. Now I give you general releases x dot equals x. And I take a solution of this Lyapunov inequality, and I do a change of basis with respect to the square root of this matrix of the concentrates, the Cholesky factor. And you do a change of variables, and then you split it into the symmetric part, into the skew-symmetric part of the symmetric. And what you get is symmetric part, which is semi-definite. And such a system is called semi-disciplinary. Or if it's positive definite, it's disciplinary. So if I give you a general x dot equals ax, I find a solution to the Lyapunov inequality. I take the square root, I do a change of basis. That means I measure in a different norm, and in that norm, what I get is that the system is semi-disciplinary. This does not change the spectrum because it's a similarity transformation. But it changes the peak of values, it changes the coercivity constants, and it changes the decay. And this is essentially never talked about in the class on ODEs. That, I mean, in the PE world, we're used to, hey, find a good norm and then everything's nice. But in the classical ODE course, that's very rarely talked about. So, why is this semi-disciplinative representation nice? So, some 20 years ago, Cedric Glani coined the concept of hypercoercivity. I only give it to you here in the linear case. So, suppose I have two matrices J and R. J is skew-symmetric, R is emission and semi-definite. Then I can define a hypercoercivity index. And that is the smallest integer m, such that the sum of j to the j, r, j to the j conjugate transpose j is. So somehow R itself is not positive definite system, it's not coercive, but by multiplying with J, you can make it points. And if M is finite, then the system is called hypercoercive. Who of you has seen the concept of hypercoercivity? It's not very well known. I understand why. The paper by Cedric Lamy is very hard to read. It's commuters from integrals, and it's very technical. But it has a very nice, so if you're interested in this, what this has to do with role theory, stuff like that. There was a paper by Franz Nachleitner and Anton Hahnemann and myself, where we make them. The really nice thing about hypercoercivity is that if you take e to the at, A is your matrix, e to the at, that's the solution operator, and you take the two norm of the solution operator, then you can show that the two norm of the solution operator for semi-distributive ODE decays right from the beginning, and from the initial value, not asymptotically, but right from the beginning, it decays by 1 minus c t to the a, and a is twice this hypercoercivity makes plus positive. So this concept of hypercoercivity gives you, Cedric designed it to do asymptotic stability, but it gives you more. It gives you decay right from the beginning and monotone. And
sorry, but then the norm can go up.
no,
After epsilon, or it decays.
It decays. It may stagnate for a while and then go down, but it will never grow.
So it was called contractive.
It's contractive. Okay. Now, what did I do? I chose a Q that satisfies the inequality. That's a linear matrix inequality that has many solutions. Many positive definite solutions, convex set. So the question is, maybe we can choose a Q in such a way that it has a best constant here, and maybe also a small hypercoercivity index, so that the system is coercive, so that you get optimal monotone decay right from the beginning. Now, I first saw proof optimization problem, because we want to minimize and Nicola optimization problem would be great, right?
We don't dislike.
But then I found in a paper on equations, I found the following result, not proof, just stated. It's the following. So suppose A has all eigenvalues in the open left half plane. So it's asymptotically stable system. And suppose mu is the largest real part of an eigenvalue of A. And you take an eigenvalue with this real part, if this eigenvalue is semi-simple, that it doesn't have a Jordan block, then there exists a Q with norm 1 such that this is 1. Now the right hand side is Q times minus 2u. And the inequality is not strict. So there's a direction where this doesn't hold. And if at least one eigenvalue is real part mu is defective, so as a Jordan block, then you cannot get it. You have to subtract mu epsilon, that is only limiting. So what does that mean? I solve this equation. inequality, rather than the original one was greater than 0. And if you solve that and do the transformation that we've done before, then the theta values set of all x, h, a, x, since here it was not 1, is to the left of the line with imaginary real part here. So from the point of view of theta values, we cannot do better. No transient behavior, theta values at the left. The resulting system is coercive. So you've turned a system that's hypercoercive into a coercive one, and it has the maximum coercivity. It cannot be better. And we have the best asymptotic decay and the C. So this representation is, in all respects that we discussed so far, optimal. But unfortunately, you have to solve for Q, and the Q is used in the transformation. And if the transformation is still conditioned, it has the inverse of the large norm, then you may have a problem. To show you this, go back to your first numerics course, and you take the ODE, and you do a one-step method to get approximations UI on the grid, on the given grid, with the step size tau I, and the method was this form, Euler's method, or the method you think of, where the increment function phi satisfies Lipschitz constitution in X for some norm, then the error behaves like time interval maximal discretization error tau at e to the LXTI minus. That's the classical result from any textbook. So the error is the error in initial value plus local discretization error times the input. If you now go to this coordinate system that we've just chosen, and you look at the Lipschitz multiplied by the Q norm of Q weighted norm of Q. So that means this representation may be optimal in the sense of decay rate, or the sense of theta values, but it may not be optimal in the sense of numerics because of this condition. So one needs to find a balance. Okay, this was all for the linear OD. Now let's go to control problems. No, first the DAs. So a DAE looks like this: linear case EX that equals AX. And I can always split it into symmetric part and symmetric part. And it's called semi-dissipative with E and R are positive semi. And such a system is asymptotically stable if the pair EA is regular. That means the determinant lambda E minus A does not vary identically, and all the eigenvalues of this pencil here have negative real part, and it's stable if all the eigenvalues are positive real part and all the eigenvalues is real part 0 are semi-stable. It's a direct extension of the classical definition. If you are interested in robot analysis, as you look at two spectrum. Suppose you have such a semi-dissipative system, EJR with R greater equal to 0 and E greater here. Then we know the following spectral properties. If mu is an eigenvalue, then the real part is less than equal to 0. If you have an eigenvalue on the imaginary axis, then it's semi-simple. let's say something about isometrics, big subsurfaces. And the other parts I will not discuss here. So very nice spectral properties right away from the structure. And there's even something like a chronic and canonical form under structure. There exists matrices, non-singular matrix L and Z, such that LEC is block diagonal, and LEC is almost zero, and E2 to A2 to this part corresponds to the ODE, and the rest is quantified equations. So, what does that mean? It means for such a linear DAE, you can always pull out after some transformation using the chronic pair by plus C of 3.18 90s to go to an ODE in principle. And we try to define a hyperproximity index for this. And the only way to do this is to define it via the hyperproximity index of this little ODE that sits here in this position. There's no definition yet. And it's an open topic now to do a good definition directly on the original data. So we just take E2, which is the positive definite, so we go to this change of variables here and take that as a hyperproximity. Now, you can consider semi. E is a possibly singular matrix, positive semi and possibly singular. So you can define a semi. And that S is a solution operator of this. Then you can give the same theorem. Solution operator in the semi-norm is 1 minus the constant times T to the A, and A is hyperproximity index. So great, same result. Big clumsy definition, but essentially we care with it. But here's a little problem with the semi-norm. Semi-norm blanks out certain components because not only zero is mapped to zero. So here's a little 4x4 problem. It's in this chronicle-like form, and the solution is 0 y2 of 0 times e to the minus t. That's the dynamical part. Y3 is y2 of 0 times e to the minus t. Y4 is 3 over epsilon. Y2 times e to the minus t. And Y4 is 3 divided by 2 by Y2. Now, if you make the epsilon very small, this can be arbitrarily large here. Still has an exponential term, so asymptotically everything's fine, but and the semi-norm doesn't see that. Because the semi-norm in this case will give you just this. So working with the semi-norm is not always the best possible way to. Okay, good. Now let's go to facility. Quickly at the end. So here's another definition of facility. So I have such a linear ODE system x dot equals ax plus u, y c x plus u, and that's called passive. If there's this Hamiltonian function such that this is equation one. And if this is strict, then it's this constant. And while in the ODE case we had the Lyapunov inequality, for the passivity we have a similar matrix inequality. It's called the Kalman-Jakubowicz-Popov inequality. So what you need to find is you take this block matrix, which is this W matrix that I have already given, and you want to find a positive definite X such that this inequality. Now that's a much more nasty inequality than the upper one. In particular, X is not appearing in all the coefficients. And if you carefully look at this, this is really a Riccati inequality rather than the upper one. And so if you take E to be X and J minus R to be XA, B to be minus C transpose plus N to B, and B like this and D like this, then you have one. So that means if you can solve this inequality, you can transform an arbitrary system into a port-Hamiltonian system and with quadratic Hamiltonian. Again, it's not really good. The set is not as nice as the Lyapunov set. We don't know the geometry of that set really is not clear. And sometimes with Paul Van Doren, we tried to find the best possible solution, and then we found out that this set is very thin and we were always on a boundary and things like that. So how do you solve this? Suppose this matrix is positive semi-definite, invertible. Then you can just do a transformation and you get an algebraic Riccati inequality. And equality case is well known from optimal control. It's a famous result about Riccati. It's a scalar case, not a matrix case. But here, observe, usually in control you have a minus sign here you have plus. And there are lots of good methods for this. There's linear matrix and control theory. There's toolboxes in MATLAB, so it's using equations. So great. There's even more. There is a solution X minus, so that F plus Gx minus is asymptotically stable. That's the minimal solution. There is a solution X plus, that minus F plus Gx plus is asymptotically stable. And any solution of the algebraic Riccati equal set is between these two points. And under some further conditions, it also showed that any solution of the inequality is between this minimum and absolute solution. And so the trick to solve this equation is now the following. So this is my Riccati inequality. And what I do now, I add a perturbation to make it an equality. And then I play with the perturbation in such a way that I get equality and that the solution approaches the boundary x minus or x plus. And the best possible solution turns out to be when x plus is equal to x minus. And that is the solution that one tries to compute. I'm not going to go to the details here. We're coming to the end. Every solution gives you a port-Hamiltonian VIA representation. So again, you determine the solution X that maximizes some optimality criteria. We tried several different ways to optimize that. We haven't found the best possible way. But in view of what we did in the Lyapunov inequality, here's an idea. So in the Lyapunov inequality, we added 2 mu x. And here we have 2 gamma x. And then we try to solve this, and we do bisection. We start with gamma equals 0, gamma 1 equals minus mu, which is the spectrum of system, because if this is supposed to be less than or equal to 0, then this has to be less than or equal to 0, and that's the Lyapunov. So the spectra abscissa is an upper bound, and then you offset. Okay. Many of these results have been extended to the nonlinear case and also to bounded linear operators. In Hilbert cases. For the unbounded case, and lots of problems. So what is the message? Port-Hamiltonian systems are great representations. If you are careful, you start from the physics, you get them for free. They're, the Hamiltonian is kinetic potential energy or magnetic energy or something like that. The physicists have known it all the way. The port-Hamiltonian formulation of a general system you can get by solving such a linear matrix. Why is this important? Still, nowadays everybody's talking about generating models with data. So then you just get A, B, C, D. And if your data come from a physics system, the A, B, C, D should be passive, and then you should be able to transform it. Open problem. Derivation theory, we have partly done, but in general, it's very difficult, very technical. We can do optimal decay rate and we can do optimal passive representations. There are similar results for discrete time and for infinite dimensional systems. I usually talk about it here. For the operator DAE case, we recently have started to work and you can also find the optimal decay rate. Numerical methods we're working on at the moment. The big problem is large scale. So you take a district as PDE, base district as PDE, you have a large scale level for you have to combine this model reduction. And then the representation we've done is optimal in the sense of decay and beta values, but maybe not in the sense of regressions. So we would like to solve some distance problem. And then if you have control and you have a system like the city of Akhlaq and most way, in principle, what we want is that every building has a feedback stabilization technology in it. We don't do that, but in Japan and in Taiwan, all the skyscrapers have feedback stabilization. And you want to be fast. So that it doesn't break down before. So that's the topic. And with this, thank you very much for the attention. And if you're interested, I can give you the slides. And also there are lots of references here